we'd like to extend our appreciation to Dr. Anna Suzuki for joining us today to speak to us. I wanted to say just a few words about her before we get started. Dr. Anna Suzuki was a tenure-track assistant professor for 5 years and became an associate professor in the Institute of Fluid Science at Tohoku University in November 2021. She graduated from mechanical engineering and completed a master's and doctorate degrees in environmental studies at Tohoku University. After receiving her PhD in 2014, she was a postdoctoral researcher in energy resources engineering at Stanford University between 2014 and 2016. Her research mainly focuses on geothermal reservoir modeling. That's very timely. Recently, she is also working as on co-creation with citizens on uses of local energy resources to promote changes in action and consciousness, and to be able to set the objective of geothermal reservoir engineering with local people. Dr. Suzuki, thank you very much for showing up and being here with us at 5 o'clock in the morning, your local time, to share your knowledge and expertise. You have the floor.
Thank you so much for having me this seminar. So yeah, it's time is 5 a.m. So my voice is a little bit weird, but please always listen to my voice. Okay, now I want to start my talk. Today I'm going to talk about the geothermal reservoir modeling combined with leading edge technology. As Mike said, I am an associate professor at Institute of Fluid Science of University. So I just promoted from yesterday Japanese time and today in US. And so I was actually I was a postdoc at Stanford, so I am familiar with living in the California for 3 years, and so I have been interested in the geothermal resources because Japan has large potential, but Japan haven't used them enough. So how should we use the geothermal energy in our society? This is my big research question. I believe that the geothermal reservoir engineering is designed a way to make a bridge between the resource and society. And I have focused on the geothermal reservoir engineering since I started my research. So geothermal energy means the hot water and steam from the underground. And I want to share the video. The video shows a very rare place where geothermal rocks are on the surface in Oyasu, Japan. So if you want to come to Japan, I want to share this place. So now we can see the hot water and steam is flow out from the narrow fracture like this. And as I showed, the flow is very controlled by the fault and fracture networks. And to understand the fluid flow in this complex blocks, we construct the simulation for reservoir modeling. The simulation model consists of the physical model that represents the flow and transport and heat. And the parameter in the physical model represent the structure. Once we construct the simulation model, we will use the model to predict the future prediction and design the development of the system. So in reservoir engineering, the constructing the simulation model is very important. So one of my studies focused on the simulation model. And because the simulation model is constructed based on the data, so the data itself is also important. So today I will talk 2 topics for the model and simulation, and 1 topic for the data acquisition. For the simulation model, there are several methods to simulate the fractured rock. As we know, the structure of the geothermal reservoir are very complex. if the complexity is not taken into account, it is impossible to represent the structure. And if the model is too complex, it is impossible to obtain the data to estimate the structure. So I think there is no single best model. So we need to develop the different type of the model with the complexity appropriate to the data obtained. To validate this model, we need to compare this model with real phenomena. And in most of the cases, the field structure are not known. So the model is tested in a laboratory under controlled conditions and compare with the data from the flow experiment. In the case of the fractured rock, the shape of the core sample varies greatly, even if it is taken from the same rock block. It is maybe difficult to ensure to the productivity and to control the shape intentionally. Thanks to this 3D printing technology, we can create a complex structure that we intend. In geoscience field, there are several studies that's produced by the 3D printer as it is. And in this study, we use the advantage of the good control of the 3D printer. We propose a method to validate the simulation model with 3D printed fracture network. Sorry. In this study, we prepared the design of the fracture network, which includes a large number of the disk shapes of fracture with different shapes. The design was used to print out the structure by using the 3D printer for the flow experiment. And the design, same design was used to run simulation with different models. First, the design was sent to the 3D printer, which is called a biscuit, and we printed the wall around the fracture network to avoid the water leakage. And we checked the precision of the 3D printed sample by the CT scanning. The left figure shows the cross-sectional image of the original design, and the next figure shows the micro CT scanning image of the 3D printed model. The white part represents the air, which means the fracture. So compared to the original image, we can create very similar structure by 3D printer. After that, we conducted a flow experiment with the 3D printed fracture network. We create a one-dimensional macro flow from the top to the bottom of the sample, and we measure the pressure difference and the flow rate to obtain the permeability. We also inject the sodium chloride as a pulse and measure the resistivity at the outlet by using LCR meter to obtain the tracer response data. Here I show the validation result. For the model, we use the equivalent permeability model, which calculates the fracture permeability by using the aperture of the fracture from this equation based on the cubic law. And the permeability, calculated permeability was set to the boundary between the grids. After distributing the permeability, we calculate a steady state, steady flow in a continuum model. We also use the direct numerical simulation using the open form to solve the Navier-Stokes equation in fine mesh. The right figure shows the comparison with the experiment and the simulation result. The yellow one is the measurement results from the experiment by using 3D printer. And the y-axis shows the permeability. The light blue one is the result of the equivalent permeability model, which shows the overestimation compared to the experimental results. And in contrast, the results of the direct numerical simulation show a very good agreement with the experiment. So, from this result, we can say that we can reproduce the same flow property in the experiment by using 3D printer and direct numerical simulation. Next, we show the comparison of the tracer response. These black dots are the tracer response obtained measured in the experiment using the 3D printer. These two graphs is the same result. The horizontal axis is the time and vertical axis is the concentration. And the left figure shows the plot of the results of the equivalent permeability model. And the right figure shows the model from the direct numerical simulation. The result of the equivalent permeability shows the early peak compared to the experimental results. In contrast, the direct numerical simulation is in good agreement with the experimental results, even for the tracer response data. So, as we have successfully validated the simulation transport model using a controllable complex structure by using 3D printed fracture network model, which was a breakthrough in the geoscience field. The research I talk today was published here. So if you are interested, please take a look. And I also put the experimental data in digital log. So thank you for the sharing this site. And if you are interested in the validation of your model, please take a look and check the fracture network and experimental result. Okay, now I move to the next topic. And if you have any question, I'm very happy to answer even in the middle of my talk. So let me know. Okay, now I move to the next topic about the topological data analysis for the fractured rock. So I told that direct numerical simulation can reproduce the fluid flow in the complex structure. However, it is impossible to develop such detailed model in the field. And the structure information is difficult to obtain from the measurement data. The structure model consists of the many parameters, such as the aperture, number, length, and density, and so on. In fact, not all the information about such structure is needed, but it is sufficient to know only the fracture structure that functions as a flow path. If we consider the flow path as a whole, which means the structure that penetrates from the one side to the other side, we can draw an intrinsic description of the rock structure related to the flow. So topology is concerned with the property of the geometric objects that can analyze the whole structure in mathematics. So we consider the flow path as a whole, and can we describe by the intrinsic information of the rock structure contributing to the flow, which is described by the whole by topology. Persistent homology is one method for computing the topological feature of the shape which provides complex and multi-scale geometric information, and it can be used to recognize the difference of the structure quantitatively. For example, the study analyzed unconsolidated rock and sandstone, and there are a little bit difference of the image. And the persistent homology can provide the difference of the structure and quantitatively. So the persistent homology now has been applied many fields. So persistent homology can recognize the flow channel connected from one side to the other side as a one-dimensional whole. So in this study, we try to investigate that if the persistent homology can describe the intrinsic information of the rock structure related to the flow. So in our study, we use the software Home Cloud to analyze the image data. There are several methods to analyze by the persistent homology, but we're focusing on the binarize the image like a CT scanning image. So persistent homology analysis provides a persistence diagram to visualize topological information from the binary image. By using the sum of the results in persistence diagram, it is possible to estimate the number of the flow channel and the minimum aperture of the channel. For example, if we have this kind of the material, persistent homology can recognize the two flow paths in the material and detect the minimum aperture of the flow, minimum aperture for each flow path, like this way. And if we assume the flow paths are parallel plate, we can derive the permeability based on the cubic law given by this equation. And this is a minimum aperture. And this value can be obtained from the persistent homology parameters. So then we try to validate the estimation equation of the permeability by using the artificial 3D fracture network and 2D 3D poor image. The artificial network was generated by our study, and we run the direct numerical simulation with this structure. The 2D poor image and 3D image are obtained from the other study. And they also conduct the flow simulation precisely. This figure shows the estimation result. And the horizontal axis is a simulation permeability from the simulation, and the vertical axis is the estimated permeability from the persistent analysis given by this equation. The orange results show the artificial fracture network, and the fracture is distributed randomly, and the blue one is the result of the fracture is orthogonal, distributed orthogonally. And the red one is the result of the 2D poor image. And the green one is the result of the 3D rock image. And the purple one is a 2D barrier sandstone. So although the results are somehow overestimated, but most of the results have correlation to the simulation data. From this result, we want to say that the persistent homology would provide a new description of the fracture structure related to the flow characteristics, especially this case is the permeability. The research has been published recently. If you are interested, please take a look. Okay, our research tried to characterize the flow path of the fractal network by using the persistent homology. And we try to find a relationship with the flow characteristics. The next step, we try to find a relationship between the structure characterized persistent homology and transport phenomena. In this study, we prepare the popular fractal network and generate each tracer response data from the fractal network from direct numerical simulation. We use the open form again. And for the direct simulation, we set the constant flow rate and we index the tracer at the pulse and measure the calculate the tracer response at the outlet. As a preliminary investigation, we focus on the peak time in tracer response. The peak time of the tracer response has a positive correlation of the cross-sectional area of the structure in the flow direction due to the constant flow condition. On the other hand, the cross-sectional area can be described by the persistent homology parameter with this equation. By using the following equation, we can try to derive the relationship between the persistent homology parameter and tracer response data. And this is the result of the comparison between the persistent homology parameter and the tracer response. So we analyze each fractal network by persistent homology and calculate the cross-sectional area using persistent homology parameter from the image data. The calculated cross-sectional area by using this equation is plotted in the vertical axis. We also conducted a transport simulation and obtained the peak time. So the peak time is plotted in the horizontal axis. If the flow path is homogeneous, the red line is the show the relationship between the cross-sectional area and the tracer response, peak time. So now we can see the black dot, which is the image data and the simulation results, mostly plotted near the red line. So since the flow rate and the apparent length are known from the beginning, so the cross-sectional area can be estimated by the tracer response by using this equation. So if so, it is possible to estimate the structure parameter expressed in the persistent homology by using this tracer peak. So when we measure the tracer response data and obtain the tracer peak, then we can estimate the cross-sectional area described by the persistent homology. At present, there is some difference between the black dot and the red line, but the future research tried to use the feature from the tracer response to estimate the structure parameters. So the target of our study is try to estimate the structure by using the measurable tracer data. Okay. Now move to the last topic, the data acquisition. So in the previous talk, we tried to find the relationship between the structure and the flow and transport. So we focus on the tracer response because it is a method that we can directly measure the fluid flowing in the structure. In the tracer test, we usually index the dye or radioactive or reactive material to the injection well and measure the concentration at the different well. And the tracer response data usually used to understand the fluid behavior, but the tracer response tells us only about the volume of the fluid, so only the volume information. As mentioned earlier, the fracture aperture is very important when considering the permeability. And however, the solute tracer cannot distinguish the shape of the fracture. It means the tracer is only give us the volume information, so we cannot distinguish if it is like a cylinder or it's like a thin parallel plate. So the fracture aperture is considered in the range between the nanometer order to centimeter order. And recently, the technology of creating the nanomicroparticle has been improved. So now we can create nanoparticle from several 10 meters to nanometer preciously. The nanomicroparticle is expected to increment the function more than conventional solute tracer because nanomicroparticles can have various material and we can control the size. So if we use the feature of the particle tracer which can control the size, we wonder if we can use the estimated fracture aperture by using the nanomicroparticle. So now I try to explain the proposed estimation method of the aperture in the fracture by using the nanomicroparticle. Now let us consider that there are three preferential paths which have the minimum aperture in the first pass, B1, B2, B3. And now we inject the particle tracer in a wide range of the sites. And the blue one describes the smaller than the B1, and the green one describes the smaller than the B2, and the red one is smaller than B3. And when the particle injects and it moves through the path 1, so all the particles can move through the path 1 in the B1. And but if the particle tries to move to the path 2, only the red one and green one is flow. And if we focusing on the path 3, only the red particle can move to the path 3. So if we can separate the concentration of the particle from each particle size, so if we inject the different size of the particle, first we obtain the peak for all of the parts, all of the particle. But secondly, we only obtain the red particle, and we can distinguish the peak with the different size of the particle. So if we can estimate the fracture aperture by using particle size with this tracer response data, so we can estimate the permeability, which gives us the velocity. And the tracer response provides the travel time. So now we have the velocity and time. It means that we may be able to estimate the distance for each four paths. So therefore, the object of our study is to verify a method for evaluating structure in a fracture by using the nanomicroparticle tracer. So in our study, we tried to do the flow experiment And we prepare the fluorescent nanomicroparticle with the size. Sorry, I didn't write, but the size is 500 nanometer made by the silica. And we use a micro model made by silicon wafer. This figure shows the micro model, and this figure is the view from the top, and this one is from the side. And we created the micro model with the matrix structure and fracture. The matrix structure contains the rock grain and the pore, which designed by the micro CT scanning data of the sandstone. We also set the one fracture between the matrix, and we inject the water from the hole, and the water flow in this black part, and we can measure the water and the tracer at the outlet. After we creating the micro model, we conducted the flow test to the micro model and observed the transport behavior of the particle by microscope. We inject the microparticle at the beginning and switch the water, and the sample was collected at the outlet over time. To measure the particle concentration, we use the Q nano to measure the property of individual particle in solution, especially particle diameter. This is a photo of the Q nano, and the Q nano has a small pore of the nano diameter. So when the particle passes through the pore, it can measure the electrical resistivity between the top and the bottom, and we can calculate the property. So this figure shows a comparison with the other method. So Q nano has the same accuracy as the TEM. So we can measure the diameter and the number of the particle. So we use the number of the particle as a concentration of the tracer. Now I want to share with the result of the observation from the microscope. So this is a micro model and fracture and matrix. And now we can observe some of the particle flow into the fracture, and also some of the particle migrate in the matrix part. Sorry, it is not obviously to observe, but now we can see the particle movement in the micro model. Okay, so now I share with the results. The left figure shows the concentration distribution of the particle diameter in the droplet at 3 hours after the injection. The horizontal axis is the particle diameter, and vertical axis is the concentration, means the number of the particles measured by the Q nano. So we injected the 500 nanometer nanoparticle in this time, but we observed that most of the particle is over the 500 nanometer. The diameter distribution is spreading, and we consider that some of the particles aggregated and come out as clumps. So we obtain the droplet at each time. So we could obtain this kind of the results over time. So we plotted each of the results in the time series of the concentration in the right figure. The horizontal axis is time, and the vertical axis is the concentration, number of the particle. So because the Q nano can provide the particle diameter, so we can obtain size-dependent tracer response. So the blue dots are the concentration of the smaller particle, like this part, and the red cross describes the concentration of the larger particle in this part. So now we expected the first particle flow in the fracture, and slow particle migrate into the matrix. The first flow is created in the fracture, and if the particle moves very slowly, we consider it migrate into the matrix. And this shows the pore size in matrix. The threshold of the 1,700 nanometer we determine is here. So most of the pore size is larger than the 1,700 nanometer. So although the small particle can migrate into the matrix and the fracture, because the particles are smaller than the pore size, but the larger particle flow only in the fracture. So our results may suggest that the different size of the particle flow in a different way. So we conclude that we can obtain the size-dependent particle concentration, which has the potential to use the estimation of rock structure. So this is my summary. So today I talk about the geothermal reservoir modeling, and my research focused on the relationship between the structure and flow and transport. So first talk about the model validation by using the 3D printer. And the next talk about the new description of the flow path based on the topology. Although it is an ongoing study, but I want to find a new reasonable description of flow and transport in the fractured media. And the third topic was about how to obtain the data from the reservoir by using the nanomicroparticle. So you can find our study in this paper. So thank you so much for kind attention. So that's all.
Dr. Suzuki, thank you so much for your talk. We appreciate. What I want to do now is I first want to give a chance to our students to ask questions before we unleash the faculty. Are there any questions from our students?
Hi, can I ask a question?
Go ahead.
Hello, Dr. Suzuki. Thank you so much for that presentation. You guys seem to be doing very interesting work at your university. Quick question. So on slide 13, you were showing how the direct numerical simulation compares to experimental results. However, there didn't seem to be good agreement after the 100-second mark. I was just wondering if you were trying to explore why there is such a gap after 100 seconds.
Yes.
No, slide 13.
13. Okay. This one. Thank you for your question. So your question is about like this part?
Yes.
Yeah, so for the simulation, so unfortunately we stopped the simulation on this until about 200 seconds. So we didn't analyze this part. So we, I think so there's a second peak of the simulation, second peak in the experimental results. So we can consider that it's one is the experimental error because the concentration is very small. So this time we measure the sodium, we measure the concentration of the cellular chloride by using the SCR method. So the condition, we cannot keep the accuracy very well, but also our fracture network model is very complex. So that's why it has the second peak. So we haven't analyzed the detail like this part. And yeah, as you said, that we should analyze we should calculate the results by using the direct simulation more a long time. So then we can figure out what happened with this one. But yeah, thank you for that question. That is a good point.
Okay, thank you so much.
Yes, thank you.
Any other questions from students? All right. Questions from anyone, including faculty?
May I?
Dr. Prodonovich, please jump in.
Thank you, Professor Suzuki. Wonderful presentation. And thanks for accepting. I know it's a V hour in Japan, so thank you for being awake.
It's good for me
giving
in the
this
morning.
presentation. I have actually here I actually thought that there was some sort of a flushing happening, or did you do anything experimentally to flush the particles? No, this is just experiment that started. Well, basically, if you can try to how does so you basically inject a wave and then you stop. There's no change in attempting to change the flow rate or anything like that to flush the concentration out. That's what I actually attributed this little peak at the end. Attempting to push things out.
Yes, so we believe that the flow rate is the constant because we use the water head difference, and we try to keep the water head difference is constant, but so during the experiment, we didn't change the head. So
Should have said
I think I'm not sure that if that has a flash there.
That's fine. That was just a smaller question on the same slide. So question also about these this model. So the way the model it was set up is that all of the fractures have the same apertures, or do they have a range of apertures with it?
For this one, yes, it has some variety of the fracture aperture. So we set the minimum aperture is 0.2 millimeter, and the maximum is 1 millimeter. Yeah.
And then they were all sort of like at the given aperture that was picked for them, they were all like parallel plates or attempting to be, right?
Yeah.
Okay.
Yeah, that's easy.
Plus minus the roughness of the printout. And what is the roughness of the printing? So I know that 3D printing has a little bit of inherent roughness to it.
Yeah, it's the fracture is located like diagonal, then the fracture have the like a
unnatural roughness.
Yeah, yeah. So the precision of the 3D printer is at 0.016 millimeter. Yeah. So it has some roughness, but we didn't consider the roughness of the fracture in our model.
If nobody has any questions, I have more.
Anybody else has questions, feel free to put your hand up and you can join the queue. Dr. Pradanovic, you're free to continue.
Well, I'll let somebody else ask. I guess
Anybody
not.
else with questions?
Ah, there we go.
Oh,
Kishore, are you?
Yeah.
There we go.
all right, Dr. Mahanti, please.
I was wondering if there are some liquids which have the same refractive index as acrylic, like dibutyl phthalate. If you put that into your fractures, the whole thing may become transparent, or then you can also visualize directly. Have you tried that?
We haven't tried to put the different liquid, and sorry, I didn't prepare the video, but we inject the water and the blue dye into the fracture network, and so now I try to reduce the number of the fracture, and so because the fracture is too many fracture, so if we reduce the fracture, then we can visualize the flow path with the blue dye. But I haven't used change the water to the other liquid, so that's really interesting. Like we can control the reflection. I think so.
Yeah.
I think it is very interesting.
Thank you.
Thank you.
Dr. Dashad, did you have a question?
Yes. Well, my question is actually more of a clarification. You mentioned that you're going to use multiple size nanoparticles to maybe find out about the structure. How do you know what should be the size of these particles that you select?
So the size of the particle, yeah. So I mean, after obtaining the liquid, can we measure the size of the particle? Is it your question?
Well, how do you decide on the size of the particles for the injection?
Before the
Yes.
the test. I think this particle. I think we need to run the normal tracer test first, and first we need to understand the well is connected. So we should know first by using the solute tracer. So then by using the solute tracer, we can estimate the apparent velocity flow rate in the reservoir. So by using the flow rate, so we should try to estimate the possible length of the aperture size. But so far, I consider we should inject the wide length of the particle for the particle tracer, and I think if the particle is too large, most of the particle is stuck before it can flow out. So we should we should consider what the size before the experiment. What size of the particle we should inject. But
yeah, so that's helpful. But at the same time, we need to be concerned about if you're injecting too many different sizes. I know the larger ones, they go through the fracture, but then is there a possibility of you actually cause plugging of the smaller pores in the matrix?
Yeah.
So I think we need to be, careful about the selection of the size and how many of them we want to inject.
Yeah, I think the concentration of the particle in the injection is quite important. Otherwise, it's stuck. And so far, I just consider only the normal particle, but in the future, even the particle will be stuck in the fracture in the matrix. But if the particle can be made by some different material which can dissolve for several time longer than the tracer response, but the shorter the month or year, then the particle, we can reduce the effect of the particle stacking.
Right.
So this is what I want to do next.
Yeah, that was actually my follow-up question, if you don't mind me jumping tailing more.
Yeah, sure, no problem.
Because if I were managing a geothermal reservoir, matrix is not so much of a concern, but if I plug my fracture network, then I'm in trouble. So is there a material that would essentially be dissolved? Because if you tailor your primary flow path, I guess about this main one, you learn everything about it in a tracer test, right? So then you're gonna design the size, or this is how I'm understanding, design the size of the particle that goes in to kind of get sort of the secondary flow path, or slightly less than this main tracer test. But that also means that some of them will get invariably stuck in there, especially if you guess the apertures really well. Then you send the particles that are similar to those apertures. But is there material, and how fast does it dissolve if I send them in, or what is the, I'm guessing in this test they're just silica, or?
Yeah, so far we just the silica and we use so now we focusing on only the transport phenomena of the particles. So we don't use any material for dissolving the for long time. But so yeah, next step, I want to find some material which can dissolve with the geothermal reservoir condition. So.
And is the main, so basically I would run this as a series of sizes, so start with the largest sizes, then follow up with presumably, possibly even plug the main path, and then follow up with the smaller ones, or is that the main idea?
My
or
idea
all at the
was
same time?
My idea was inject the wide range of the particle and what once, but as you said that if we can separate inject different size, that is better for to avoid the stacking. So yeah, I think that now we try to do the experiment with inject the constant particle size, or inject the wide range of the particle size, and we try to see what happens in the flow, how affects the if we inject the same size of the particle or different size of the particle, how to affect on the stack inside of the matrix and the fracture. we try to observe it by using the micro model so far.
Okay, thank you.
Yeah, currently we haven't the finish of the experiment yet, but we wanna check how much we have the effect.
Thank you very much, Dr. Prodanovich and Dr. Delshad. Any other questions? We got time for a question or two.
Yeah, if there's time, I'd like to ask one more.
Sure, go ahead, Barun.
Hi. So going back to the same model simulation portion of your presentation, you had 3 bar graphs, which basically showed that the direct numerical simulation was far more accurate than the continuum mechanics model. My question is, what's the computational cost of both models? Are they relatively close, or is the direct numerical simulation a lot more expensive by orders of magnitude?
Yeah, it's definitely very different. The equivariant permeability model simulates very short time, and the direct numerical simulation has to use the supercomputer, and it has a very high computational cost. So my idea is we can also say that direct numerical simulation is the best way to characterize the flow in the fractured media because it's too expensive computational cost. So we have to find the good way to describe the complexity, and so it should be in between. But we need to validate the model. So then we want to use our experimental data to validate each model to describe the flow in the complex structure. So that is my message.
Okay, thank you.
Yeah, thank you.
All right, that gets us about to 4 o'clock. Once again, Dr. Anna Suzuki, thank you very much for joining us at 5 o'clock in the morning, your time, and for spending time sharing your knowledge and expertise with us. And we appreciate that very much. One of these times you have to come visit us in Texas. Don't stop at California.
Okay, yeah. Next, I go, just go to the Texas.
Awesome.
Yeah,
Thank you very much. Everyone stay safe.
Yeah, thank you.
Thank you.